So, for this first graph, we got a velocity versus time graph, which is what we were going over on Friday. Okay, and we learned that on a velocity versus time graph, obviously you can read velocity at various points in time. And from that, we can calculate things like acceleration. Okay, if we know the initial velocity and the final velocity and the time, we can calculate acceleration. Okay, and we can calculate the displacement. And we calculate the displacement by understanding that displacement equals average velocity times time, which on a graph that's irregular means calculating essentially the area between the line and the x-axis. Okay, because between 0 seconds and 4 seconds, the car does what? Or the object does what? Well, actually, it's doing something. It's traveling at a constant velocity of positive 4 meters per second. That means its average velocity during that time is positive 4 meters per second. And so if I go average velocity times time, I get that it goes 16 meters during that time. Is everybody all right with that? Okay. Now, the rest of the graph, I got to do pretty much the same thing. Basically, I've just got to divide it up into shapes that I can calculate the area of, and each shape will have an average velocity and the time. Okay, so I'm going to look at probably this triangle here, this rectangle here, and then this little triangle at the end. Okay, that would represent all of the things that I can calculate. All right, so let's do this big rectangle first. During this big rectangle, the average velocity is 2 meters per second. Everybody all right with that? Okay, and that goes on from 4 to 12, which is 8 seconds. So 2 times 8 is 16 meters. Okay, what's going on during this part of the graph where the line is diagonal? It's slowing down. Okay, so that means since it's slowing down from 4 meters per second to 2 meters per second, the average is right in the middle. Okay, everybody all right with that? Average would be right in the middle there. Okay, so if I'm looking at this, the height of this triangle goes from 4 to 2. Okay, so the height is 2 and the base is 4. All right, so 2 times 4 is 8. Divided by 2 is 4. Okay, and that's all we're doing. We're looking at the height. The velocity in here changes from 2 to 4. Okay, the height of that triangle is 2. The base of that triangle is 4 seconds. 2 times 4 over 2. Okay, everybody all right with that? And then our last triangle here, we go from 0 to 2. Okay, so that's a height of 2, and the base is also 2. 2 times 2 is 4. Because it's a triangle, divide by 2. Okay, and we got our 2 there. All right, so we got 32, 36, 38 meters. Okay, that's probably still more than I would ask you to do on an exam. I would probably on an exam give you one that had at the most 3 shapes to calculate. Okay, does everyone follow what I did there? This is a very common thing to be asked on a test. Okay, very, very common. All right, so this one is a position versus time graph. All right, we learned about those last week as well as what we did our lab on yesterday. This one is also irregular, meaning I can't use y equals mx plus b here because I don't have one linear fit. Okay, so I want to find the average velocity of the object over the whole trip. So the first thing I've got to understand is that average velocity is total displacement divided by total time. Okay, how do I calculate displacement from a position versus time graph? Final position minus initial position. My final position is 10. My initial position is -4. Right? 1, 2, Yeah, 4 is negative 4. All right, so final position minus initial position, okay, is going to be 10 minus negative 4. The change in position is 14 meters, and it's positive because it goes from negative 4 to positive 10. Okay, so its change in position is 14 meters. What's my total time? 14 seconds. What's my average velocity? 1. Positive 1 meter per second. Remember, you've got to have a vector on that. Okay, so our average velocity is positive 14 meters divided by 14 seconds. That's positive 1 meter per second as our final answer. Okay. All right. Graphing is probably the trickiest thing in this unit. It's one of the 2 trickiest things. Okay? There's a lot of interpretation that goes on in graphing. Right? So we need some practice at it, obviously. Okay? And the plan today was to practice doing some graphing stuff and really work on that. Okay, have you guys try one, me do it, okay, and that kind of thing, just so we keep getting that repetition of, okay, I did it right, or here's what I missed, so I don't miss it again. Okay? So, okay, so we did those position versus time graphs. We did that one at the end of the day on Friday, I think. Yeah. Okay, so I would like you guys right now to try this one. Okay, so velocity versus time graph. Don't worry about the rounded edges. Just imagine that's sharp corners. Okay, for the rounded edges. I want you to find the total displacement over the whole trip, the average acceleration between 5 seconds and 15 seconds. Just as a reminder, acceleration is final velocity minus initial velocity divided by time, so that'll help you with that part. Okay, and the average speed over the whole trip. Okay, so a lot of it is like what we did on the first question on the practice quiz there. Okay, so give it a try, okay, and see how you do. I'll give you a few minutes here to work on that, and then we'll look at it together. Okay, how many people for part A went ahead and did all the shapes? Okay, nothing wrong with that, but I want to show you something about graphical analysis. If you found the shapes, I'm sure you got the right answer. But there's a way to do this that involves not having to do any math at all and just analyze the graph. Okay? So in the first part of this graph, right here, the flat parts, okay, so this part right here, what's the object doing? Traveling at a constant velocity. Oh, Julie, can you let him in? For some reason the door's locked. Probably because I didn't unlock it. I'll own that. That's my mistake. Okay. So in the first part of this graph, the object is traveling at a velocity of -8 meters per second. Right? What's going on in this slanted section of the graph? It's accelerating, yeah. Okay? It's accelerating positively. Its velocity is becoming more and more positive. Okay? So it starts at -8, okay, and eventually becomes +8. And then for the last part of this trip, it travels at +8 meters per second. Are this part of the graph and this part of the graph mirror images of each other? Does that mean that it did exactly the same thing in a negative direction as it did in a positive direction? It does. If it did that, doesn't that mean its displacement would be 0? Yeah. Okay? So that didn't require me to do any math. I just looked at the graph and went, okay, what's going on here? These two parts of the graph are identical, but one's positive and one's negative. That means they cancel each other out. That's all I had to do. Okay, without doing any math, without doing any shapes, okay, I was able to come up with that answer. Now, I have to do the shapes in order to get was average speed over the whole trip in part C, so it's not like you did work unnecessarily. You were going to have to find the area eventually anyway. I'm just saying that if there wasn't a part C, that question could go a lot faster. In fact, I've made that a multiple choice question on a unit exam before. Here's a graph. What's the total displacement? Okay, if you analyze the graph, you can do that question probably 3 times faster than doing it mathematically. You'd still get the same answer either way, but I'm saying it's time saving if I recognize and can analyze graphs. Okay, everybody with me there? All right. So, since we have to do that whole area calculation anyway, we'll end up doing it in a few minutes. All right, for part B, it wants to know the average acceleration during the part of the graph where acceleration occurs. So between here and here, okay? So that acceleration lasts for 10 seconds, okay? And if I'm just plugging into this formula here, my final velocity is 8 minus my initial velocity of -8, okay? And that lasts over 10 seconds, right? So I'm gonna have 16, positive 16 divided by 10 is going to give me positive 1.6 meters per second squared. Now, we haven't talked about acceleration yet, so I don't want you to get confused about that squared. It doesn't mean the number is squared, okay? It doesn't mean what, 25.6 or whatever it comes out to. Okay? It doesn't mean that, okay? 2.56, sorry. It doesn't mean that. It means the units are meters per second, okay? So it looks like this. The units for acceleration are the rate of change of velocity, meters per second divided by seconds. If I set that up like a fraction, it looks like this, meters per second. If I divide fractions, what am I supposed to do to divide fractions? Okay, yes, reciprocate and multiply. Right, okay, so we want to reciprocate and multiply. So I'm just going to take that second one, instead of being seconds over 1, it's going to be 1 over seconds. And then I'm going to do that first thing you said, we're going to multiply the top, and then I'm going to multiply the bottom. Okay, what's meters times 1? Meters. Anything times 1 is itself. Okay, so meters. What's seconds times seconds? Seconds squared. That's where we get that unit from. It's quicker than writing meters per second. It's also quicker than saying meters per second and having people think that you stutter instead of meaning something else. Okay? So, we say meters per second squared because everyone understands when you say a unit is squared, it actually means it's divided by itself. Okay? Everyone all right with that? All right, so that's how we did part B. And then for part C, we had to calculate the average speed. Average speed is total distance divided by total time. In order to get the total distance, I actually have to calculate the total displacement and then just make everything positive. So that means doing the shapes. All right, do I need to bother calculating the ones on the top? No, I already know they're the same. So again, I can save myself some work. Okay, this is going to be -8 times 5, that's 40. This is going to be -8 times 5 divided by 2, 20. 60 plus 60 is 120. 120 divided by 20 seconds is 6 meters per second. Okay? Everybody all right with that? Yeah? Shapes everywhere. Go for it. There are so many shapes. Okay? I'll give you a few minutes. Just see if you can get the shapes drawn. Then I'll draw the shapes. Then we can get to the math. Okay? Okay, so in this first part of the graph, between point A and point B, what's the object doing? It's accelerating. Its velocity is going from 0 to 20 meters per second. So our first shape is going to be that triangle there. Okay? Then, what does it do here between B and C? Travels at a constant rate. So we're going to have this rectangle. Okay? Because when something travels at a constant rate, its average velocity is the height of the rectangle. Okay? In the case of the triangle, its average velocity is half the height of the triangle because it's changing from the initial value to the final value uniformly, so the average is halfway in between. All right? Now, in order to simplify things, rather than draw like a whole bunch of little tiny shapes, I try and draw as many as possible. Since I know I'm going to have to calculate basically the whole area underneath this graph at some point, okay, I'm just going to start drawing as these kind of big shapes. Okay? This is one really big shape. Okay? I'm going to calculate that whole rectangle when it asks about the whole trip. Obviously for part A, for part B, it's only asking between A and E. So I'll actually have to cut that off right here. Okay? And I would, let's say, do this rectangle, this bottom rectangle, and that little triangle, as well as this triangle. Okay? Over the rest of the trip, obviously, we've got these two other little triangles here and here. Okay? So that's up to you. Okay? I would say between A and E, you're looking at four shapes. Two triangles, two rectangles between A and E. Right? How many people have done A already, part A, about calculating the acceleration? Okay, let's quickly look at that. All right, this is the formula we have to remember. It is on the back of your periodic table, which you're probably going to want to have out the remainder of the unit, because on the back of it are all the formulas. This is one of them. A equals VF minus VI over T. Okay, so when we do this, okay, we've got VF, okay, which is 20, positive 20, minus our initial, which is 0, and that takes 2 seconds. 20 over 2 is positive 10 meters per second squared. Okay, acceleration is a vector quantity, so we should indicate that with a positive sign. All right, I'll leave you to work on part B. Give you a few more minutes before I do the math of it. Okay, at least you've got the shapes now, so you can kind of get going on that. Okay, that analysis that I did to arrive at those shapes is the same thing you should be doing. Okay, this is accelerating, this is traveling at a constant velocity, this is accelerating, this is traveling at a constant velocity. Let's get our shapes in there. Okay. So if I'm going to calculate the total displacement to E, which happens at 8 seconds, okay, I've got to calculate the area of these shapes because each area will represent the average velocity times the time. So for our first one here, it goes, it's got a height of 20 and it has a base of 2. 20 times 2 is 40. Okay, divided by 2 is going to be 20 meters. So we know that triangle there is 20 meters. The next shape we have drawn is a rectangle that represents a constant velocity of 20 meters per second for the next 6 seconds. So 20 times 6 is going to be 120 meters. Okay, and then we have this small triangle above, okay, and it goes from 20 to 40, so its height is 20, its base is 1 second, 20 times 1 is 20, divided by 2 is 10 meters, okay, and then we have this rectangle where the object travels at a speed of, at a speed of 40 meters per second for another 3 seconds, okay, so when I'm calculating this box, I don't go all the way to the x-axis because obviously it doesn't either. Okay, so the height of this box is 20. That occurs for 3 seconds. So that's another 60 meters. Okay, the reason I don't take this all the way down is because I've already calculated this part. Does that make sense to everybody? Okay. So now I take these numbers, 140, 210. Yeah, so 140 there, 200, 210 meters. Okay. That's our, actually that should have a positive on it. Why? What did it ask for? Displacement. Is that a vector quantity? It is. So that should have had a positive on it for sure. Okay. Part C wants us to find the acceleration between F and G. That's easy. 0. Okay. I don't need to do a calculation to prove that. I just need to look at it and go, well, it's flat, so the velocity isn't changing, and since acceleration is a change in velocity over time, it's 0. Okay, so that's a nice easy one. No calculations required there. All right, part D wants the average velocity between A and F. To calculate average velocity, I need total displacement and total time. Do I have most of the work done for this already? Yes. I just got to do a little bit of extra geometry, okay, right here. To get the rest between the beginning and F, between A and F. Okay, so give you a minute or two to get that done, and then we'll walk through it. And then they want the total distance traveled, which is the last bit of geometry, okay, on the graph to do. Okay, so give you a few minutes, then we'll look at those together. Okay, so going to F means getting these other two shapes right here. Okay, constant velocity of 20 meters per second for another 2 seconds. Okay, so 20 times 2 is another 40 meters here. Okay, and this is 20 times 2 over 2, so this is 20 here. Okay, so we add on to that. What do we have? 210 before. We add on another 60 for 270 meters in total. Okay, and then we divide that by 10 meters per second, so we get, or sorry, 10 seconds, so we get positive 27 meters per second. Right? Everybody okay with that? Okay, don't be afraid to ask, guys, if you got questions. Okay, so for the last part here, because it asks what's the total distance traveled, we just have to finish out the graph. So I'm going to extend out and get another 40 meters here. How did I know that was 40 without doing any calculating?
It was the same size as the
Exactly, it's exactly the same size as the one beside it. So again, just analysis to save time. Okay, and then we've got a base of 1 second and a height of 10. 10 times 1 is 10, over 2 is 5. So add another 45 on, and we got 315. Is that right? Okay, I shouldn't do math. Yeah, I shouldn't do math in my head, but I was right. So that keeps rewarding me to make me do math in my head more. Okay, you always forget the ones you do wrong, and you remember your triumphs. Okay. All right. Questions on that one? Obviously, a question like that is incredibly tedious, right? I mean, there's nothing like innately hard about any individual step, but there's just so many steps.
Would there be anything like that complex on the unit test?
It's not that it's complex; it's that it's tedious
Just
and
like
time-consuming. Yeah, I would never. Like on a unit exam, you'd probably get something like, so here's a velocity versus time graph. I might give you something like this. Yeah, like I just need to know that you can do that, not how fast can you do it and how many of them can you do. That I don't care about. Do you remember how to do this? This shows me you know how to do both parts, and I'm good with that. Yeah. Okay, so the question might ask, what's the acceleration here, and what's the total distance traveled, or what's the average velocity? Something that wouldn't take you very long to do. Okay. Okay. Let's take a 5-minute break, and then we'll do this one. Okay? You guys have been working pretty good. So let's take a 5-minute break, and then we'll do this one. Okay, let's have a look at a few things on here. So the first, for part A, they want us to calculate the acceleration between 7 and 9 seconds. So acceleration is final velocity minus initial velocity divided by time. Okay, we already know that the time is going to be 2 seconds because they told us it's between 7 and 9. Okay, and then I'm looking for the final velocity, 0. minus the initial velocity, positive 3. Okay, so 0 minus 3 is negative 3. Divided by 2 is negative 1.5 meters per second squared. The negative is important. It's slowing down. That's what a negative acceleration indicates in this case. Right? Questions on part A? Okay, how many people have done part B? So for part B, we got to do all the shape things again between 0 and 7 seconds. So I got to get to here. All right, so I would say there's probably, let's say, that big rectangle. Triangle, triangle, rectangle, rectangle. Okay, I think that's the least amount of shapes we could do it in. All right, so this little triangle here, 1 times 1 is 1, divided by 2 is 0.5. This rectangle here, 1 times 3 is 3. Okay, this triangle here, it's 2 on the base, and it's 2 high. 2 times 2 is 4, divided by 2 is 2. And then this rectangle here is 1, 2, 3 on the base, and it's 3 high. That's 9. Okay, so 11, 14.5. Positive 14.5 meters. Okay, is our total displacement to 7 seconds. If it wants us to calculate the average speed over the whole trip, I need the total distance divided by the total time, which means I have to also calculate this last triangle. So 3 high, 2 wide, 3 times 2 is 6, divided by 2 is 3. Okay, so that adds on to our total there. What do we have? So we got 17.5 meters, is that right? Okay, so 17.5 meters divided by 9 seconds is going to give us 1.94 meters per second. Anybody all right with that one? Okay, and then the last thing, the average, or the acceleration between 2 seconds and 4 seconds. So that's this part right here. Okay, so again, acceleration is VF, 3, minus VI, which is 1, and that takes 2 seconds, which is why we get positive 1 meter per second squared. Okay, questions on any of that? Okay, let me give you an idea how I might ask stuff about this question. Certainly I might ask you to do similar to what you did here. Here's something else I often do, and it's a 1-mark question. I might say to somebody on a test, what is the acceleration between 4 and 7 seconds? That's a 1-mark question. What's the answer? 0. You would be shocked to see how much work people will do to prove what the acceleration is. Not 0. So they'll go through all this math that's wrong, okay, to prove something that should have taken them 2 seconds to realize. So I'm just saying, caution here, that's an analysis question. It's not a calculation question, okay? And I often mix the two in the same question, okay? So that's a matter of, this is a velocity time graph, and in that part of the graph, the velocity is not changing, thus the acceleration is 0, not a equals vf minus vi over t. Although if you do that, you should also get 0. But it's crazy to see how many times people will do a bunch of math to show me something that's not right. So just caution on that. Analysis is important. Okay, tomorrow we are going to talk about acceleration. Okay, we're going to work on acceleration tomorrow. Thursday, we're going to be doing a data analysis activity. Okay, kind of a lab, kind of not. And then Friday, more acceleration. And then on Monday, we'll be moving on to the second half of the unit on energy and work. Okay. If you're struggling with any of this stuff, guys, make sure you're popping in for help.